Good afternoon, everyone. It is my pleasure to introduce Kateryna Foyetsova. She is coming to us from University of Notre Dame, but before getting there, she got her bachelor degree in physics from Lviv National Polytechnic University. Then she crossed the pond to get her master thesis at Minnesota State University, after which she again crossed the pond to go to Germany to get her PhD at the University of, I have my cheat sheet, Goethe
Um,
Universität Frankfurt am Main.
yes, Frankfurt University in short.
And then she crossed the pond yet again to do her postdoc at the University of British Columbia. And then she traveled just a little bit to get her assistant professor position at the University of Notre Dame. And today she's going to tell us about molecular physics without molecules and flat band quantum materials. So it's all yours.
Okay, thank you, Helena, so much for the introduction and for the invitation to have for this opportunity to discuss my research with you. So yes, today I would like to talk about this subject, which is molecular physics without molecules in flat band quantum materials. So now here's the outline, and as you saw in the title, I had several keywords. So I feel like in the introduction, I have to talk a little bit about each one of them. So I will first talk about quantum materials. I will give my definition of how I see quantum materials. Then I move on and change the subject quite a bit and have a couple of slides about molecules because we need to understand some of the molecular physics to proceed. And then I will try to show you that we can actually marry together quantum materials and molecules and get something that is known as flat band quantum materials. So I will also explain to you what a flat band material is. And then I will show you some examples of flat band quantum materials with which I got to work recently. So my first example is going to be this intermetallic system, titanium 4 manganese bismuth 2. The system behaves as a one-dimensional chain of localized magnetic moments with spin 1/2, which are submerged in a sea of correlated electrons. I will show you that the system has many interesting properties, and I will argue that they actually can be understood when we consider the fact that we have molecular physics in the system. And then I will have, if time allows, a second example. So this is going to be one of the recently discovered nickel-based superconducting systems, lanthanum 3 nickel 207. So again, for this system, I will show that because of the molecular physics that we also have in it, the properties of the systems might be much more similar to those of the cuprates than what it might look like at the first glance. And in the end, I will give a summary. All right, so let's start with quantum materials. Now, to give some motivation, I should mention that material science in general has been extremely important. So it has led to many discoveries that actually changed our world. Let me give you this simple example of silicon. We know that silicon is the material that we use to make microchips, which are the key components of every electronic device. Right, so this is quite impressive. So what we achieved using this relatively simple material. And I have to say that this material is not even considered to be quantum. Now we have quantum materials on the other hand. I'm going to give a definition in a few seconds. But just to, again, motivate all the excitement around the quantum materials, just think about what we can achieve with systems that have much more exotic properties compared to the simple silicon, if with silicon we were able to achieve this much. So quantum materials, what are they and why everyone is so excited about them? So quantum materials are materials in which the quantum mechanical nature of the constituent particles, which are electrons and nuclei, so that quantum mechanical nature leads to it gives rise to very exotic, sometimes non-trivial emergent quantum phenomena. And those quantum phenomena can be measured and observed at a macroscopic scale. Let me give you some examples. So the prototypical quantum material with um, such properties would be the metal, the mode insulator. So it's a system that shows metal insulated transition. This phenomenon has been studied a lot. It has a fundamental importance in its own, but it can also be used for gas sensing, for example. And then we have quantum magnets that, again, there's a range of them with very different and interesting exotic properties. And some of them even have, they actually have diamagnetic interactions give rise to quasi-particles that are known as Majorana fermions, which is something that nowadays has potential application for quantum computing. And then we have quantum materials with appealing electrochemical properties. Those are used in lithium-ion batteries, again, something that we have around us everywhere. And then, last but not least, high-temperature superconductors. So this is something that people are still, working on, and not really fully understanding what's going on in most of these high-temperature superconductors. But if we are able to design a high-temperature superconductor that would be superconducting at ambient conditions, we would be able to apply, so to use it in things like transportation and electricity transmission. Now, let me spend a couple of minutes talking in a bit more detail about one particular family of quantum materials. So this is going to be the superconducting cuprates. So it's a family. They all share, so they all have copper in their structure, and they all have very similar phase diagrams, which feature a lot of very interesting exotic phases, including the superconducting phase. So this is a typical phase diagram of a cuprate. I have doping here, which is essentially the amount of strontium you introduce. And then you have temperature on the other axis. And as you can see, when you vary the doping and the temperature, you can tune your system into a variety of very different not fully understood quantum phases, including the pseudogap, strange metal, and of course the superconducting phase. Now, as I said, we don't always understand the superconducting mechanisms in quantum materials, and the cuprates is one such. So this is where we don't have an understanding as well, but we do understand something. So we know that so the known fact is that all the cuprates that have a similar phase diagram, they have copper in their structure. And those copper atoms and the oxygens, which are also always present, they always form these two-dimensional planes. As you can see here, this is the side view, and now this is just one plane, the top view of it. So this is the plane that is that every cuprate system has. And what we know is that the superconductivity somehow originates in this plane. And what we also know is that it's the copper atoms that actually give rise to, they provide the electrons that end up getting paired in and form a superconducting state. Now, what I'm trying to do now is to, again, simplify even more and come up with an effective model that would contain only the most important, the essential ingredients, the bare minimum for us to understand some of the properties of the system. So as I said, we need to have the copper atoms. It is important that they are arranged in this two-dimensional square lattice. So this is what I'm showing here. Now we keep simplifying things. So we assume that for us or for distributed technology, um, we only need one electronic state per copper site. It has a certain symmetry and a certain name. So in this picture, I put a dot to show that each copper will have only one state available for the electrons to go to. And then those electrons that can be in these atomic states, they are allowed to hop from one state to the nearest neighboring one with some hopping probability T. And then the final ingredient of this minimal model is going to be the on-site Coulomb repulsion between two electrons that happen to come to the same site at the same time. And this is what I label with U. So even though we don't understand fully what's going on, we do know that the proper description of the properties of the system should be based on this simple model. Now, you can write this in the form of an equation. This model has a name. It's the Hubbard model. And as I said, it has essentially two terms, the electron's kinetic energy and the electron's interaction energy, with the parameters T and U. All right. So this is, for this talk at least, all we need to know about quantum materials, and in particular strongly correlated quantum materials that can be mapped onto this Hubbard model. Now, let's change gears and talk about molecules. Right, so it's a completely different beast. Molecules are different from solids because molecules are always atomic clusters of finite size. And the simplest molecule you can think of would be the hydrogen molecule, H2. This is the AI image I obtained from ChatGPT. And now here's the model that I want to use to talk about the molecular physics that we can have here for this molecule. So like before, I'm going to have in this model atomic sites. I'm only going to have two sites for this model because, well, I have two atoms. And then I'm again going to have only one state available for the electrons on each side, right? So that would be these two red dots, the electronic states, and they're going to be the hydrogen's ground state, 1s, 1 and 2 for the two different hydrogens. And I again allow the electrons to hop from one side to the other. And I will call this a Hubbard-like model because at this point, at least, I'm not interested in any interactions. I just want to see what happens if I model my hydrogen molecule using this simple model with these simple assumptions. So for this system, the Hamiltonian is extremely simple. It's just a 2x2 matrix in the basis of these atomic states. And by diagonalizing this matrix, you obtain the eigenstates of the molecule. And there are going to be two of them, the bonding with the low energy and the anti-bonding one. Now, you can describe all that using this energy diagram. So before I had my hydrogen atoms interact, I just had two isolated hydrogens. These were the energy levels of these states, each with one electron. And then I switched on the hybridization. I got these molecular orbital states, and here's one, the bonding one, the anti-bonding one. They both are some linear combinations of the atomic states I had at the beginning. Now, my two electrons that I have in this problem will occupy the lowest energy state. One will spin up and the other will spin down. And from this diagram, you see that the system is stable because if you calculate the energy of the electrons before the interaction and after, because of this energy lowering, the hydrogen molecule is going to have energy compared to the energy of the two independent hydrogens. So that's essentially all we need to know about molecular physics for this talk, at least. Now I'm gonna show you how those two, the quantum materials and the molecules, or molecular physics in molecules, um, can be combined, and this is what happens in flat band materials. All right, so for that, I'm going to start again with the hydrogen molecule. Now we know what happens. We know that we have these two states, and the electrons are in this bonding state. Next thing I do, I'm going to go from a molecule to the simplest solid again you can have, which would be just a one-dimensional chain of hydrogen atoms. Okay, so I call it a solid because it has the essential property of solid. So it has this periodic arrangement of the atoms in it, even though it's one dimension. So you see there are no molecules. You can think of this as an infinitely large molecule, but that's not how we usually approach this problem. Now, we know that when you have a system like this, these energy states that were just energy levels in the beginning for a molecule become bands with certain widths, right? And the second thing that happens in a solid is that the electron's momentum k becomes a good quantum number. So you can talk about the k dependence of the electron's energy. And typically, you would use a plot like that to show that dependence. So for this system, these two bands would have this sign-like dependence on the electron's wave vectors. And then, so now we know we have molecules, we have bands. Now it's time we start talking about flat band materials. So these materials are periodic systems, just like this one, but and they have bands. But under certain conditions, it happens that some of the bands become extremely flat, extremely narrow. So they start resembling the states that we typically expect to see in molecular systems, like this one here, which I show as a molecular-like state. Now, for that to happen, you need to have a special geometry that would enable a special type of constructive and destructive interference effect between the wave functions of individual atoms. So those geometries are very non-trivial, and that certainly doesn't happen when you have just a chain. But I want to give you one example of a system where that happens. So this is this pretty famous bilayer graphene system where we have just two monolayers of graphene, which so one is twisted by a certain angle with respect to the other. And when you are at that angle, in the band structure, you get an extremely narrow, very flat band like what you see here. In the inertial states, you would see it as a feature like this. Now, so this is one example of a flat band material. And they are not so common, but there are certain patterns, certain geometries in 1, 2, and 3 dimensions that give rise to those flat bands. And in this paper, for example, they look at several one-dimensional flat band geometries, models, essentially. So here, schematically, we have, again, sites that are connected by hoppings, just like I had in my examples. And these are all the geometries in 1D that in the band structure have a perfectly flat band. Now, what they actually show in this paper is that every time you have a flat band in a system that doesn't really have any clusters in the structure, any molecular-like clusters, you still can associate that flat band with a localized state. And if you look at this configuration, for example, this flat band would be associated with a localized state where you have a plus and minus combination from the wave function of these two sites. Okay, so again, we have these localized states, and people have been very interested in these, especially recently. But the problem is, let's say, it's a very interesting problem of material science, but also it's an interesting mathematical problem. So people were approaching this problem from different directions. And that's the reason that we have, at this time, more than one name for this phenomenon. So in this paper, they call these localized states phenostates. Other groups that specialize in slightly different areas of condensed matter physics, they call these states compact localized states. Now, in my circle, so with my collaborators who work on this problem, we are used to using this term, molecular orbitals. But they actually just different names for the same phenomenon, for these localized states that you can associate with a flat band in your system. So in my talk, I'm gonna always use molecular orbitals when I will be talking about these kind of states. All right, and the last part of my introduction is when I try to show what can happen when, in addition to flat bands, you have some correlations. So correlations is that on-site Coulomb repulsion that I had in the very beginning when I was talking about the cuprates. And I said that for some time I'm going to ignore it, but now I'm bringing it back. So let's have a look again at this chain. This can be hydrogen or anything else, but we do have only one state or orbital per site. I have my hopping as before, but this time I allow to have electrons to interact when they come to the same site, and that will be described with this U. Now, in the case when this interaction is weak and the hopping is strong, the electrons are going to behave quasi-independently, and even if I have one electron per site, I'm going to have a metal. And so I'm going to have a metal, and people would say that we have a Fermi liquid. So it's a electron quasi-particles that move quasi-independently, and all the interaction between the electrons can be described in terms of some mean field that each electron would feel. Now, in the opposite regime, where my interaction is large compared to the kinetic energy, it becomes energetically very unfavorable for the electrons to hop around, because when they do hop, there will be times when they come to the same site at the same time where they start interacting, and that will increase the energy of the system. So in order to avoid that, what happens is that the system freezes the electrons. And in the case we have one electron per site, there will be exactly, this will be the electrons frozen in this way, one electron per site. And the electrons are frozen, so there will be no electrical conductance. So the system becomes an insulator. So conventionally, people think that all the quantum materials can be positioned continuously on this correlations spectrum. Now, I'm gonna claim now that that's not the case when you allow for the possibility of having those molecular orbital states in your system. And in order to illustrate that, I'm gonna look at this system now. So it's, again, a new variation of this chain system I had before, but this time I'm gonna have not one single orbital, but two orbitals per site, a red one and a blue one. And I'm gonna have two distinct hoppings the large one and the small one. And they will be arranged in such a way that for each channel, the blue and the red, I will have an alternation of the large and small hoppings like this with some shift. And if it happens that the large hopping is larger than my interaction and the small hopping is much smaller than my interaction, um, I won't be able really, to place this system on the spectrum. But what will happen is that this is going to be the largest energy scale. So we have to consider this, these two orbitals connected with the large hopping first. And this resembles very much the hydrogen molecule situation I showed previously, right? Two sides coupled with some hopping. So what happens first is that those two atomic sites will get hybridized and they will split to give us again two molecular orbitals, the bonding and the anti-bonding one. That will happen for both the blue orbitals and for the red orbitals, and there will be a shift. And now if I have again exactly one electron per site, those electrons are going to occupy these bonding molecular orbitals. But now because I have my interaction, these electrons are not going to be hopping around, but like in this case, they will get frozen here on these states. And the important difference is that here those localized states are the atomic states, whereas here they are the molecular states. And we have localized molecular states here in this periodic system, which, in terms of structure, does not have any molecular clusters. And so I'm gonna now go over and talk about this system. At this point, I just wanted to mention that this is a very oversimplified model for what happens in this intermetallic system I'm going to talk about now. So that's the work that we did recently, and it was published. And I would like to acknowledge, of course, the contributions from these wonderful people. So they are George Zawadzki, Megan Aronson, Alberto Nocera, and Xiang Li from the University of British Columbia. And also Noah Leip, who was my summer student, and he comes from the Dickinson College. So this is the system that has flat bands and those molecular orbital states, but I feel like I have to really introduce all the experimental situation before I talk about that molecular orbital physics that we figured is there in the system. So this is the structure. We have two so-called strongly correlated transition metal atoms, titanium and manganese. These are normally associated with strong correlations. Now, the manganese atoms form one-dimensional chains that run along the z direction. And the titanium atoms form squares. So these are the white balls, squares that are centered at the bonds connecting the manganese atoms. And then as I go from one bond to the next one, those titanium squares are going to be rotated by 45 degrees. And that happens every time I go to the next bond. So in this picture, I use the red and the blue colors to represent two different orientations of my titanium squares. Now, as many intermetallic systems, this system is a metal, as you can see here, which is probably the only kind of normal property of the system, because when you measure its magnetic properties, you find that it behaves as a paramagnet with a magnetic moment that corresponds to spin 1/2. And this is something that you do not expect to see in a system containing manganese atoms, because manganese atoms or ions, they almost always are in a high spin magnetic configuration, which is spin 5/2. So that was a real puzzle to see this behavior in the system containing manganese. Now, the system doesn't order, at least that was never detected in experiments. So there is a possibility that it ends up in a spin liquid state, which is a quite interesting quantum state. Now, it also has very unusual spin excitation spectrum. I'm showing it here, but I will not talk, explain why it's unusual. So I will say that for later. And also, this is a system where we have both localized magnetic moments and itinerant electrons. And if you have a system like that, there is a possibility of the quantum physics. And last but not least, this is a system that has flat bands. Those flat bands, they were seen in this experiment, for example. This is an experiment. It's called angular result photoemission spectroscopy that allows you to measure the K dependence of the electron's energy. Now, the color map that you see is the result of the measurement. And I have here, close to the Fermi level, a feature that might be a flat band. Now, the lines that you see is calculations, which actually agree quite well with the measurements. And indeed, this feature is a flat band that we have very close to the Fermi level. So when I was invited to join this project, my task was to use my theory, which is called, so the methods I use are based on density functional theory, sometimes also called ab initio theory. You can do things with that kind of theory. You can, in particular, calculate the same kind of band structure as you measure in this experiment. So this is what you see here. It's a very messy band structure, but what's important is, again, in agreement with the experiment, we see the flat bands very close to the Fermi level in the calculations. Now, so we wanted to understand, first of all, how it happens that the system has localized magnetic moments of spin 1/2 instead of 5/2. And second of all, we wanted to understand what is the origin of this flat band. So we knew that it has to be some sort of localized molecular orbitals. So with the band structure that's as complicated as this, it's really difficult to actually do that analysis. But what we did was first to try to see what's the nature, so what is the atomic composition of this flat band. And in DFT, it's easy to do that. So I saw that in this flat band, I have basically a lot of contribution from these two manganese orbitals with these symmetries, x squared minus y squared and xy. In the density of states, this flat band and a couple of more other flat bands show up as sharp features, which is typical for a flat band system. So because of the complexity of the band structure, we were not able to really establish a quantitative model, but we did some qualitative analysis that helped us figure out what's the nature of those localized states. And I would like to walk you through that very quickly. Now, so this is the chain, the manganese chain I have in the system. And as I mentioned, I know that the important orbitals are these two, the red and the blue ones. This is how they look like in real space. They are the d orbitals with the d, with these symmetries. Each manganese has both red and blue orbital. And I also know that these titanium orbitals are important. And the next thing I want to know is how these orbitals are coupled. I cannot calculate the couplings, but I can use a picture like that to see the pathways or the pairs of orbitals for which the coupling is going to be the strongest. And this always happens for orbitals which are spatially close together. Like these two orbitals, they have parts that are pointing towards each other. So I know that for these two orbitals, I'm going to have a very large hopping. Now here I have the same red orbital. It's very strongly coupled to this titanium orbital. But because of this 45-degree rotation, this red orbital cannot couple to anything on the other side, right? Because there is no such red orbital available. But for this square, when I look at the blue orbitals on the manganese, they do have the titanium orbitals that they can couple with. And that would be this pair, for example. What I just said can be shown using an energy diagram like this, where I have the atomic energies on the manganese atoms. This energy representing the four titanium orbitals here. And I know that the coupling is very strong between these. And this is what I'm going to have here. And it might not look like it, but actually, in terms of couplings, this looks very similar to what I had for the hydrogen orbital. Hydrogen molecule. I have a cluster-like situation, but now in terms of orbitals, not atoms, where I have orbitals very strongly coupled inside the cluster and not coupled to anything outside. So we know now what should happen in such a case. I should have my molecular orbital states that result from linear combinations of the participating atomic orbitals. I'm going to have three such molecular orbital states in this case. And there will be three of those for on each bond. But I use different colors just to highlight or emphasize the fact that I have this rotation. This is how those molecular orbitals are going to look like in real space. This is the lowest energy state, and the filling in the system is just right to give to have exactly one electron per bond occupying this lowest energy molecular orbital. And because of the strong correlations now, these electrons are going to be localized, and they will give rise to these magnetic moments that would have spin of 1/2 because they come from just single electrons. All right, so from this point on, we know what to do with the system. We can do a mapping onto onto a spin model like this. There will be some interaction between my spins. And in this expression, I have two parameters, the coupling and the anisotropy. And depending on the values for these two parameters, the excitation spectrum, the spin excitation spectrum will look quite differently, which is something that we used to analyze the experiments done by Xiang. So he used inelastic neutron scattering to measure the excitation spectrum. And it was now Alberto's part to do the simulation. So he was able to find the parameters of that spin model that were giving a very good agreement with the experiment. So these are the numbers. I said them actually don't really have time to go into details here, but the numbers are there. He was also able to calculate the entire phase diagram for that model as a function of the interactions and the anisotropy in our system is found to be a boundary of different quantum phases, which means strong fluctuations, quantum fluctuations, and that probably adds to the richness of the physics of the system. Now, the work that Noah did is what I have here. So everything I explained, I I told you was so that explanation was qualitative. Let's we just look at the orbitals in real. We didn't really have the numbers for the hoppings to confirm our assumption that that should be the largest one, and this is where we would have our molecules. But when Noah came, I gave him this task to try to come up with a model. So he had to go through many approximations, and he was able to produce a simple model with only three orbitals, with which he was able to describe the three bands which we think are most important, and they're shown here in black. And what's most interesting is that in this model, we have a flat band exactly at the Fermi level. Um, um, Surprisingly, the numbers that he got were not what we expected. So we were expecting to see a large number here and some much smaller number for these hoppings, which, as you see, is not what we have in reality. But that only makes system even more interesting because it means that the nature of that localized state is quite is not as trivial as we thought originally it was. Now, Noah also noted that in terms of interactions, our system can be mapped, onto one of those well-studied one-dimensional flat band models, which is this one here. And in the end, we should include, of course, the other channel. So if you only have the hoppings, the red channel and the blue channel are not interacting, and you can treat them independently. So in this full model, I would have 6 orbitals, 2 flat bands at the Fermi level, 2 electrons to go to the flat bands, and then I have to switch on the correlations, which I know are important. And it's the correlations that actually couple the blue and the red channel. And that would be, the model that we suggest for the system. And I think it's kind of model that hasn't been studied so far. So it would be great if someone gets interested in looking at the properties of this model. So it looks like I don't really have time to go into any detail in relation to my second system, the nickel superconductor. So skipping the introduction, where actually I'm showing that the nickel-based superconductors are related to the cuprates, the copper-based superconductors I showed in the beginning. And we have two distinct members in the nickel-based family, the infinite layer nickelates and these bilayer nickelates. So the infinite layer nickelates are similar to the cuprates in terms of the crystal structure and also the electron count. This system is different because it has bilayers and also different number of electrons in the 3D orbitals. What I was hoping to show you, but it looks like I don't really have time, is that despite these differences in the structure and also in the electron filling, because of the molecular orbitals, which is something I show in this slide, because of the molecular orbital splittings of the same kind I had in the hydrogen molecule system, I can have a situation, so let me go straight to that here, where I have molecular orbitals in the electronic structure, and that changes the occupation of the most important orbital for the superconductivity in both the cuprates and in the nickelates, the x squared minus y squared orbital, which in the cuprates is half filled, and in this system is quarter filled if you don't do the molecular orbitals properly. But if you do the molecular orbitals properly, you look at this kind of splittings, and you can have a state where the occupations will be just right to produce the x squared minus y squared band, which would be exactly half filled. And that makes this system much more similar to the cuprates than what it looks like on the surface. This is just to show you that in my density functional theory, I can stabilize a state like that. And in this slide, again, I'm looking at different magnetic configurations. I find that the ground state configuration is not, unfortunately, well, for me, the one that has the molecular orbitals because of the very complex competition of the molecular orbital physics and interactions and other effects. So it's this state that is the ground state, but I think this is still an open question whether, like, and to what extent the molecular orbitals are important here. All right, and that brings me to my last slide. So I hope that I was able to convince you that molecular orbitals do not always need molecules to form. We can have them in solids, and this is actually when things get interesting. So when we do have them in solids, they always show up as flat bands. Flat bands in their turn mean strong correlations, which is only one of the many intriguing effects that molecular orbitals can bring along in a quantum material. And I showed you two examples, one only shortly. But in those two examples, in each case, it was the molecular orbitals who were actually making a big qualitative difference. For this system, it was the molecular orbital kind of physics that was changing effectively the effective magnetic moment from spin 5/2 to spin 1/2. And for this system, it's the molecular orbital physics that is changing the important occupations, and in this particular case, it will be from quarter filling to half filling. So that's all I had for today, and I would like you to thank for your attention, and would be very happy to answer your questions.
Thank you, Kateryna, for this very nice presentation. So let's start with questions. Could you please raise your hand, use the lower button in the Zoom to ask questions, please? Okay. So I do not see currently any question. Let me ask one question. So you were mentioning in one of your initial slides about mean field approximation that you are using in your Hubbard model, if I remember well. Does this mean Hartree-Fock essentially?
If you are, so I think it was maybe here.
Yes, it was. Yeah, in this one. Yes, exactly.
So at this point, I'm that was. So that was just a general discussion of
Okay, it was not related to a specific method then.
it was not related really. It was just
Okay.
to point out that we have these two limiting cases. So in one, you have a Fermi liquid where electrons, well, they this effective mean field, right? And their behavior is not really correlated. We can describe it in terms of a Fermi liquid. That's what I was trying to say here, right? So the method that I use, and it's something that comes a bit later, when I, yeah. So the method that I use is density functional theory.
Yeah, this I got later. Yes. No,
Um,
it's clear. Yeah.
yeah,
Okay, and what did you meant by correlation spectrum in the previous slide again? What do
that
you
one.
mean?
So um, so that is just me saying that you have these two limiting cases, but of course, in quantum, well, in materials, you can have all sorts of situations, right? You can have a situation where your kinetic energy and the interactions are comparable, right? They are
Mhm.
similar in strengths. So it's not only these two extreme cases, but you can have materials that are in between. And this is what I meant by the correlation spectrum,
I see.
right? So when you tune the ratio between U and T, you can,
Mm-hmm. Take.
I mean, that's the, I think like conventionally, maybe people think about this way. But
Mhm.
then I argue that if you have a situation where you have two energy scales associated with the kinetic, with the hoppings, right? The large one and the small one, and then your U is somewhere in between, then you cannot really place such a system anywhere on this correlation spectrum, where you
I see.
basically have only two parameters, the bandwidths, the kinetic energy, and the interactions.
Yeah.
And
Okay.
yeah.
Okay. Thank you so much. So let's continue because we have some questions. Maybe George can ask first.
Yeah, thank you for the talk. I have two questions. So, do materials with a flat bands have some particular transport properties? And the second question is, do flat bands appear in particular places in the band structure, or it's something arbitrary? Thank you.
It is something arbitrary in I let me go to this. So maybe this helps me because it's a specific example of a system with flat bands. So it has flat bands in more than one place in the band structure, right? So it has a flat band at the Fermi level, but it also has a flat band at lower energies, right? So these are the occupied states. So when you have those molecular orbitals and they are a result of these, like these cluster-like hoppings, then you always have not just single molecular orbital, but they there will be as many molecular orbitals as you have um, as there are atomic orbitals that are forming your molecular orbitals, which means that you are always going to have more than one flat band in the band structure. So in this particular case, that would be, let's say, the anti-bonding orbital. But if there is an anti-bonding orbital, there has to be a bonding one. So this would be, I mean, it's an oversimplification for this situation, but I just want to make a point that it's perfectly possible to have more than one energy, so more than one flat band in the band structure. But the most interesting and important case is when they are close to the Fermi level or at the Fermi level, exactly as it is the case here. Yeah. So that's why we actually focused on this flat band. The reason was that it was the flat band exactly at the Fermi level, even though it has more than just this flat band.
Okay, great. Maybe Alexei can ask his question now.
Sure. Maybe I'm missing something. I can think of a very simple way to generate flat bands systematically. So how about take a material that has a pores, like a porous material, or has a like rather large air cavities, like a cage structure. And inside if each cage, I put an atom or molecule, whatever, that has a very well-defined energy level. Now, the way I look at the structure then is that from a tight binding model perspective, I have a periodic arrangement of this, let's say, atoms. They each have a level, and they're all the same in all the cavities. They are relatively far apart from each other. So each cavity separates the atoms by a large distance. And then what you have is a tight binding model says, okay, there's a same level in all of this cavity. They're weakly coupled, so there will be a little bit of a band formation. But that band will be very narrow simply by tight binding argument. You have very little interaction. So you can look at this as like a different structures, maybe to identify these, or maybe systematically make this, take a porous material, with the cages, and introduce a dopant that sits in those cavities, and then you have your flat band.
That is of course a way to get flat bands, but those would be the flat bands that I would call trivial, because if you look at something that's not trivial, and I have those here, I believe. Right. So the most interesting cases is when you don't really have any atomic clusters, any isolated atomic clusters that you can identify in your structure. So if you look at these examples, it's just, as I said, this quantum mechanical interference effect that give rise to a flat band. So these are most interesting, but of course, what you described would also, qualify as a flat band system. And in the system that I had, this titanium system, in the structure itself, we don't see any, again, atomic clusters. We do have clusters of orbitals. So it's a case which is a little bit less trivial to the case when you have just isolated clusters in your periodic solid. But the least, or the most interesting, the least trivial case would be something like this, right? So you don't have, it just, so geometry does matter a lot. So you can have a periodic structure without any molecular-like units, but still have.
Okay, great. Maybe Halina, you can continue.
Yeah, I kind of want to follow up Alexei question. So in case when you have one atom and then a cage of other atoms, even though they are flat bands and Katya, you say these are trivial, but these materials sometimes called cage compounds are not that trivial. They have a very large thermoelectric power, right? So they would be good ZT material. Maybe they are trivial in the sense of this kind of physics, but not so trivial. I mean, they are still very useful compounds.
No, absolutely. When I was saying trivial, it's in the context of flat bands only, right? So flat bands, yes, of course. I mean, like these kind of systems, they have, I'm pretty sure, very interesting properties of their own, not related to the flatness of the bands.
Well, the question I wanted to ask, how would one, so you show here 6 different cases for non-trivial or interesting flat bands. How would one go about and look at different crystal structure and determine which one would give you a particular one? Would that be, it would be not an easy, I guess, case, but could there be some systematic approach to finding any particular one?
Yes, so I know that that work has been done. People have tried to approach this systematically, but they only looked. So, like for example, it's I don't know what came first, but I know that there are certain geometries that are known to produce flat bands. And I think it was that, people first look at the geometries and establish that there are flat bands, and not that they found the flat bands in some materials and traced it back to the geometries. But for example, Kagome systems in 2 dimensions, they under certain conditions again. So you need to have the right. So in this lattices, for example, all the hoppings are equivalent. So it's the same. You would use the same parameter for all these bonds, right? So if you go away from that, then you lose the flatness in the band structure in that band. So, and what I was trying to say is that, so this, I think, in materials, I think it's a bit, more complicated. So you can, for example, look, it's not that structurally, well, you can look at the structure and maybe do some analysis similar to what was done in this system, and come up with the recipe for what kind of structures might have the right geometry for the flat bands. But you actually will be missing a lot of systems that potentially can have flat bands, because orbitals have to be treated separately. So like in this example I had, the titanium system, it was just a simple chain, like in the hydrogen case, the hydrogen example I showed. But because of the presence of those titanium squares and the hoppings and all that together, and the orbital orientations and the symmetries of the orbitals involved, it's not just the structure that matters, but also the kind of orbitals that are important.
The atoms that are there and what kind of
The
orbitals they contribute, right?
that are close to the Fermi level and things like that. So it's, at this point, it's don't really have all the answers. It's something that's being, very actively explored. And as far as I know, people have looked at models. I think that more work has been done in relation to models, rather compared to what was done with real materials. It's not, so you need to have that, those, you need to have the hoppings to have the right values in your material to produce a flat band. And we were just lucky to come across this system that had the right, the right interactions and the orbitals to have that flat band.
Yeah.
Okay, great. Is there any last maybe question?
I have one more question if no one else has question.
You can maybe ask it because we don't have any other. Please.
So when you showed the phase diagram at the end, there was ferromagnetic state, or is that not ferromagnetic state? Yes, that one. So this is just the it's a phase diagram for a titanium for manganese bismuth too, or this is just some general phase diagram, and the 412 falls onto that corner.
So this is when I realized I have to go faster. So so this is the spin Hamiltonian that used, and then it was found that we have 2 exchange interactions, and these 2 parameters, so they are they measure the anisotropy in the interactions for each, the first and the second nearest neighbor. And now this is the phase diagram for that model that has 2 exchange interactions and some anisotropy in the second nearest neighbor exchange.
I see.
So this is the ratio between these 2 exchange interactions on this axis, and this is the anisotropy here. So this is it's more like it's a phase diagram for the for the model, but not for the system. And in
I
this
got
way,
it. I got it. And then your the
Please.
412 is just that dot there with respect to based on the ratio of J2 to J1. And what is VC?
Oh, this is a phase that's called vector chiral. So I think it's when your spins form this chiral structure as you move. So there's rotation as you move along your chain.
Thank you.
Yeah.
Okay, great. So let's thank Kateryna again for the nice presentation.
Okay, thank you so much.
Thank you.
Thank you.